So far, we have discussed several differential equations derived by applying Newton's second law of motion. Also, we talked about differential equations that model population growth, population dynamics. And what I want to do now, I'd like to introduce a differential equation based on a simple observation about how fast a hot object loses temperature in a cooler environment. And the basic observation is that the greater the temperature difference, the faster the object will cool. For instance, if we put a boiling pot of soup in the freezer, it will cool down much faster than if we simply leave the pot on the counter, right? So to be more precise, suppose we have a hot object like a coffee mug. This is our hot object. Think of a coffee mug. Right? And let's call the temperature y of t. This is the temperature at time t. This hot object, our coffee mug, is cooling off in a room whose temperature, let's denote by T0, T naught. So you have your hot coffee mug inside the room, and the room temperature is T naught. This room temperature is fixed, but the temperature of the coffee mug is changing with time. That is why I wrote it as y as a function of T. So every time I say hot object, think of a coffee mug inside the room, and the room temperature is T naught. And what people observed is that the rate of change in the temperature of the coffee mug, the rate of cooling, is proportional to the temperature difference between y of t and T naught. So this is the key thing, the key observation from like based on what's happening in the real world. People observed that physicists observed that the rate of change in the temperature, the rate of cooling, the rate of change in the temperature is proportional. Temperature of the coffee mug, the rate of cooling of the coffee mug is proportional to the temperature difference y minus T naught. The difference between the temperature of the coffee mug and the ambient temperature, the temperature of the room. Y of T minus T. Oh, so this is the basic physical observation fact that we know. And how can we translate this into the language of mathematics? Now, you all know, as soon as you see this term, rate of change in the temperature, rate of cooling, that is telling you about the derivative with respect to time. So what this observation is actually telling us in terms of mathematics is that the derivative of y with respect to t, this is the rate of change of the temperature of the coffee mug, the rate of cooling, rate of change in mathematically expressed, it is proportional to some constant multiplied by, proportional to here means some constant multiplied by the temperature difference, y minus T naught. And I need to put a constant here to the left of y minus T naught. I'm going to denote my constant by negative k to emphasize that this constant must be a negative number. In a moment, I will explain why we should expect this constant to be a negative number. But before explaining that, let me just tell you that physicists, they call this constant k, they call this the cooling constant. It depends on the physical properties of the object, of the coffee mug, the material of the coffee mug, for example. So the constant, this constant is a positive constant. Negative k will be a negative constant. The constant k greater than 0 is called the cooling constant. and it depends on the physical properties of the object, on the physical properties of our coffee mug. Properties of the object. What about the units for this K? It's 1 over time. Units of K, 1 over time. Okay. Now, let me also explain why I had this negative sign. So my claim is that this constant of proportionality must be a negative number. Let me give you a little bit of explanation about that. Why do we have a negative sign? Negative sign. Folks, before explaining that, this equation, which describes the rate of change in the temperature of our object in the room, this is sometimes referred to as Newton's law of cooling. Let me also write the name of this. It's known as Newton's law of cooling, which actually makes perfect sense. Now, why do we have this negative sign? Going back to the negative sign. So, my friends, I want you to notice that when the temperature of the object is greater than temperature of the room, if y of t is greater than t naught, what does that imply? If the temperature of the object is greater than the temperature of the room, we expect the object to lose temperature, right? That tells me that the object is going to lose temperature, is going to become cooler, will lose temperature as time passes by. As time goes on, y of t will decrease. So that tells me that y of t is a decreasing function in this case, is a decreasing function. And so what is the expectation about the derivative of y when you have a decreasing function? So in this case, you should expect dy dt to be less than 0. And that is what this negative sign is doing for me. When y, look at our equation, look at the Newton's second law, Newton's law of cooling. When y is greater than t naught, I want dy dt to be negative. And that is what the negative sign is doing for it. Also, we can use this law for the case where y is less than T naught. When the temperature of the room is greater than the temperature of your object. For example, you have a cold a glass of cold water in the room, and now in this case, it will gain temperature. The temperature will increase as time passes by. The water becomes warmer as time passes by. You can use this law for that case as well. So maybe calling it Newton's law of cooling can be a little bit misleading. It can be Newton's law of cooling or Newton's law of warming, right? So let me also explain that case. So if y is less than T naught, you have cold water, like you have a glass of cold water, then the expectation is that y of t will be increasing, will be increasing, an increasing function in this case, increasing function, right? The water becomes warmer as time passes by, right? The water becomes warmer as time passes by. And so in this case, we expect dy dt to be positive. And this is exactly, again, what this negative sign does for me. When y is less than t naught, y minus t naught is negative. Negative times negative will give you a positive number. So I explained the negative sign. And let me also make a quick comment about the solution, the general solution of this equation, and then I will solve an example. So what is my comment about the general solution of this equation? How to solve dy dt equals negative k times y minus t naught. There are multiple ways to solve this. For one thing, you can view this as a first order linear equation and then solve the equation. However, I'm gonna introduce like a clever way to solve this equation. What I'm gonna do is that, so let me actually write that down. There are multiple ways to do this. There are multiple ways to solve this equation. You can view this equation as a, for instance, you can solve this equation. You can solve this equation as a linear first order equation. We have a step-by-step procedure for solving linear first order equations. So here I'm gonna use a trick. Alternatively, or you can solve it as a separable equation, but here I'm gonna use a trick which makes things a little bit simpler. Alternatively, if we let u equals y minus t naught, introduce u as y minus t naught, then we can rewrite our equation. Then we have du dt. Notice that T naught is a constant number. The temperature of the room is a constant number. So du dt is exactly the same as dy dt. Du dt and dy dt are exactly the same. And then on the right-hand side, we have negative ku. And this equation, we all know that we memorize the solution to. This is one of the most fundamental equations that we need to be familiar with. Let me again, I think this is not the first time that I'm talking about this particular equation. This particular equation also you can solve as a separable equation or a linear first order equation. However, again, I'm gonna recommend everyone, I want to suggest to everyone to memorize the solution to this one basic equation. If you have du dt is equal to some constant times u, if the rate of change is proportional to the current value, then the solution is an exponential. I have gone over this many times. C e to the alpha t. This is the general solution. C is an arbitrary constant. So I immediately know from this that u of t is c e to the negative kt, where c is an arbitrary constant at this stage. This is the general solution of our ODE. And so what will be y of t? Notice that u is y minus t naught. So this is telling me that u of t, which is y minus t naught, u of t, let me write it as a comment here. U of t is equal to y minus t naught, y of t minus t naught. Therefore, what I have here is that y of t minus t naught is equal to c e to the negative kt. And that tells me that y of t is equal to t naught plus c e to the negative kt. So this will be the general solution to the equation that we call Newton's law of cooling, right? T naught is the ambient temperature, the temperature of the room. At this stage, C is an arbitrary constant, and K is the cooling constant. It depends on the physical properties of the object. So let's solve like a simple example. Applying this law that we just learned about how an object, the temperature of an object changes in an environment with fixed temperature T naught. So let's say, let me go to the next slide. So here is our example. A cold beer, this is a cool example. A cold beer initially at 35 degrees Fahrenheit warms up to 40 degrees Fahrenheit in 3 minutes. Okay, while sitting in a room of temperature 70 degrees Fahrenheit. So the ambient temperature, the temperature of the room, our T0, big T0 is 70 degrees. and we have our cold beer inside the room, and the initial temperature is 35 degrees Fahrenheit, and after 3 minutes we have 40 degrees Fahrenheit. In a sense, it is warming. It is warming up this cold beer. How warm will it be? Will the beer be if left out for 20 minutes? So that is the question that we want to answer. So here is my solution. The first thing that I'm going to do, I'm going to give a name to this quantity of interest, to the variable of interest. Let y of t be the temperature of the beer after t minutes. Okay, very good. So what are the pieces of information that we have? It is given to us that y at 0 is 35, y at 3 after 3 minutes is 40, and what are we asked to do? We are asked to find y at 20 after 20 minutes. We want to see what is the value of y when t is equal to 20. So how do I do that? I'm going to use the law that I just learned about. I know that Newton's law of warming in a sense here. So we have, based on what we just discussed, the rate of change in the temperature of y is proportional to the difference in the temperature of beer and the temperature of the room. The temperature of a room is 70. The constant of proportionality we denote it by negative k. Okay, very good. And previously I discussed why negative makes sense here. K is a positive number. So what is the solution? I just solved this for you. We noticed that if we solve this, the solution will be y of t equals T naught, the temperature of the room, plus C e to the negative kt. This is the general solution to this equation. At this stage, I don't know what C and K are. I'm going to use the pieces of information that are given to me to determine C and K. Once I have C and K, I can compute y at 20 after 20 minutes. So I'm going to use my first piece of information. I know that y at 0 is 35. So that tells me that what is y at 0 when t is equal to 0? I will have 70 plus c times e to the negative k0. That is y at 0. This is equal to 35. E to the 0 is 1. So 70 plus c is 35. So c is equal to negative 35. 35 minus 70 is negative 35. So I have my c. That's good. That means that at this stage, I know that y of t is equal to 70 minus 35 e to the negative kt. I still don't know what k is. In order to find k, I'm going to use the second piece of information that was given to me, the fact that y at 3 is equal to 40. So y at 3 after 3 minutes is 40. That means that 70 minus 35 e to the power of negative 3k when t is 3. When t is 3, we get e to the negative 3k. This is equal to 40. Very good. So what does that tell me about negative 35 e to the negative 3k? That is equal to 40 minus 70, which is negative 30. That means that e to the negative 3k is equal to 30 over 35, which is equal to, if you divide by 5, 6 over 7. Excellent. So what does this tell me about the k? I can actually compute k here. It's very easy to compute k. But what I really need to know is this e to the negative k in order to have a formula for y of t. That is the real quantity that I'm interested in, not k itself. I can compute k by applying natural log to both sides of this equality, but that is unneeded. I don't need that information. What I really need is e to the negative k. So here I have e to the negative k to the power of 3 is 6/7. So e to the negative k is the third root of 6/7. 6/7 to the power of 1/3. And now I can have my y as a function of t. Y as a function of t is 7 minus 35 e to the negative k to the power of t. And I know what e to the negative k is here. This is 70 minus 35. E to the negative k is 6/7 to the power of 1/3, and then to the power of t. So this is equal, that means that y of t at any time t after t minutes, the temperature is 70 minus 35 times 6/7 to the power of t/3. Now, the question asks us to compute y after 20 minutes. Y of 20 is equal to 70 minus 35, 6/7 to the power of 20/3. Now, use a calculator. I think it's approximately equal to 57.5 degrees Fahrenheit. Awesome.